Hello there, Mr. Sutton here with the BC Calculus 710 Part 1 homework solutions on the alternating series test. For this problem, we're trying to figure out if this series converges absolutely, conditionally, or not at all. So the first thing to realize on this is that if you have cosine and you're doing, this is going to be pi, 2 pi, 3 pi, you're basically alternating back and forth between -1 and +1. So this really can be rewritten as -1 to the, let's see, is it n or n plus 1? Well, cosine to the 1, that would be -1. So if we make this to the nth power, then that'll flip us back between negative and +1, starting at -1. All right, so this is what the series really looks like for all intents and purposes. Now, to figure out the absolute versus conditional convergence, we first take a look at this thing without the alternating. So this would just be, in that case, 1 over radical n. So this is a p-series. The p-value on this one, if you rewrite this with an exponent, is going to be 1/2. And since 1/2 is less than or equal to 1, this diverges by the p-series test. So it does not converge absolutely. So now we look again at the alternating version of this, and we see that the terms of this are going to be alternating, and also since the denominator is growing faster than the numerator, which isn't really growing at all, it's also going to be decreasing to 0 in absolute value. So since the terms of the original are alternating and decreasing in absolute value to 0, we would say that this would converge conditionally by the alternating series test. For number 7, we want to know for what integer k, where k is greater than 1, will both of these two series converge. So we'll take them one series at a time and see what kind of k values we need to make this happen. For this first one, we have an alternating series. In order to make sure that it stays alternating, we have to make sure that this k value is an odd number, because that would give us actually an alternating series. If k were even, then this -1 would automatically become positive and we wouldn't have an alternating series anymore. So if it's an alternating harmonic, then we're good. So k value has to be odd. Moving on to the next one, this is a geometric series, and we know those converge if we have a common ratio, an r value of less than 1. So if we want less than 1, that means this k value needs to be less than 4. So, for example, 2/4 or 3/4, that would work out for us. And this, again, would let us converge by the geometric series test, common ratio less than 1. So we need odd and less than 4 and greater than 1. Well, the only odd number that meets all those conditions is 3, so that's choice D. For this problem, we want to know all values of x for which this series converges, so the interval of convergence. Since this is not a geometric series, we're going to have to use the ratio test and set the result of that less than 1. So I have the n plus 1th term, that's going to be x plus 2 to the n plus 1 over radical n plus 1, over just the nth term, so the original here. And same change flip, we have x plus 2 to the n plus 1 times radical n in the numerator. And then in the denominator, we have everything else. We have the radical n plus 1 and the x plus 2 to the n. Can't do anything with these n's just yet, but I can reduce this exponential term. So subtracting the exponents, we're just going to have an x plus 2 in the numerator along with the radical n. And then we still have that n plus 1 in the denominator with nothing else because this x plus 2 to the n got canceled out. So now as n approaches infinity, we can forget about this little plus 1 inside the radical. Radical n over radical n is just going to reduce to 1. So we just have this x plus 2 left over. And now I can set that less than 1 for my interval of convergence. This is going to be my preliminary interval of convergence. I don't know for sure whether this is going to work out, but let's go with this. So I can rewrite this as -1 less than x plus 2 less than +1 without the absolute value. Subtracting 2 from everywhere to get x by itself, I have -3 less than x less than -1. And I'll put a question mark because I'm not really sure that's the final interval of convergence. Since we did this with the ratio test rather than the geometric series test, we have to test the endpoints for convergence. So if x is -3, let's see what that does to our series. That would be -3 plus 2, which is -1, over, well, -1 to the n over radical n. So this one alternates and decreases in absolute value to 0 since this n is growing down here, which means that this converges by the alternating series test. And now let's check out the other endpoint, -1. So -1 plus 2 is just 1 to the n, which is just 1. So we have 1 over radical n for that series. Now this is a p-series with an n or p-value of 1/2 because of the exponent down here with the radical. Since that's less than or equal to 1, this diverges by the p-series test. So at the end of the day, we can write -3 less than or equal to x, which is just less than -1 because we diverged at -1. And that's going to be which answer choice? Well, we have equals followed by not equals, so that's going to be choice B. For this problem, we're trying to determine whether this converges or diverges. So first thing to notice is this is an alternating series with this -1 to the n power, and the terms are also decreasing in absolute value to 0. This denominator that's growing is going to drag us down to 0. So because we have alternating and decreasing in value to 0, that means this series converges by the alternating series test. For this problem, we want the interval of convergence for this series here, and they're using k's, notice, instead of n's, but otherwise it's pretty much just your normal interval of convergence problem. Since this is not geometric, that means we have to use the ratio test to start this thing off. So I have limit as k approaches infinity of my n plus 1th term inside absolute value. So we have x plus 1 to the k plus 1 over k plus 1 squared. And now we have also under that, we're going to have just the nth term. So this is n plus 1th plus nth term, or over nth term. So this is just going to be x plus 1 to the k over k squared down there. Multiplying by the reciprocal, same change flip, we've got x plus 1 to the k plus 1 times k squared in the numerator now. And in the denominator, we have k plus 1 squared and x plus 1 to the k. Can't do anything with these k's and squares. However, we can reduce the x plus 1 to the k exponents by subtracting the exponents. So in the numerator, I just have x plus 1 to the first power and a k squared. Denominator, this whole x plus 1 to the k got canceled out, so we just have k plus 1 squared. And now, as k approaches infinity, I can ignore this plus 1 next to the k in the denominator. So I've got a k squared down here, a k squared up here. Those can cancel, leaving me with just x plus 1 inside my absolute value. Now for my interval of convergence, I'm going to set this less than 1. And I can rewrite this without the absolute value by writing -1 less than x plus 1 less than 1. And then let me just subtract 1 everywhere to get x by itself. So I have -2 less than x less than 0. Now I'll put a question mark here because I need to test the endpoints still. So now testing out -2, that would give us, let's see, if I plug in -2 for x, that would give us -1 to the k over k squared. Now this is a series that is alternating, and since we have this k squared down here, this is decreasing in absolute value to 0. These are all the terms that are required to meet the alternating series test, so this converges by the AST. Now for the other endpoint, 0, if I plug that in up here, I've got 1 to the k, which is just 1 over k squared. Now this is a p-series with a p-value of 2. Since that's bigger than 1, that means this is going to converge by the p-series test. So for my final interval of convergence, I can write -2 less than or equal to x, because we converged by the AST on that endpoint. And then I can write less than or equal to 0 because we converged again by the p-series test. So that ends up being choice E. For number 12, we want to know which of these series converges. So let's look at these one at a time. This first one is a p-series with a p-value of 2. Since that's greater than 1, this converges by the p-series test. Option 2 is the harmonic series, which we already know diverges without doing any further work. Option 3, these terms are alternating and decreasing in absolute value to 0 if you take the limit of the nth term. So this is going to converge by the alternating series test. So then at the end of the day, options 1 and 3 converge. So that's choice D. For number 13, we're told the power series given here has a radius of convergence of 2, we want to know at which x value can the alternating series test be used to verify convergence at x. So for the alternating series test to be usable for verifying this, we need two things to be the case. First off, we need to be within the interval of convergence for that x value, otherwise you won't be able to verify convergence. And you also need an x value that makes this thing alternate. All right, so let's go ahead and find that interval of convergence. Now, the good news on this one is we've already got half the work done for us. They told us the radius of convergence was 2. So we just need to take x minus 5 and set the absolute value of that less than 2, because this is going to give us our center here. So we can write negative 2 less than x minus 5 less than positive 2. And we know that we're starting at 5 and then going 2 to the left and 2 to the right of that. So we've got 3 less than x less than 7. Based off of that interval of convergence, we can eliminate any x values that are not at least at the border of this, right? So 2 is too small, so is 0, so is negative 1. Right away, C, D, and E are out of here. So now 4 and 6 are in this interval of convergence. Which of these can actually be used with the alternating series test to verify convergence? So if we plug 6 in to the original series, we've got 6 minus 5, which is going to come out to 1 to the n. That doesn't alternate. So although you might be able to prove that we're converging at 6, you won't be able to do it with the alternating series test. You would actually have to use something else, like perhaps a p-series or some kind of comparison test, or the ratio test maybe. However, if we plug in x equals 4, well, now 4 minus 5, that's going to come out to negative 1 to the nth power. This alternates. So that means then that choice B is our best answer on this one. For this no calculator free response, we have some function g, derivatives of all orders, and a Maclaurin series for g, given by this series right here. So for our first task, using the ratio test, we want to figure out the interval of convergence for this Maclaurin series. Well, they told us to use ratio test, so here we go. We need the limit as n approaches infinity of absolute value of, and now we need the n plus 1th term, so that's x to the 2 parentheses n plus 1, close parentheses plus 1 over 2 parentheses n plus 1 plus 3. So a whole lot of n plus 1s in parentheses. All of that craziness over just the nth term here. Now let's do same change flip, and I'm also going to simplify this a little bit. So in the numerator, I've got x to the, let's see, this will be 2n plus 2 plus 1, so 2n plus 3 times 2n plus 3. Next, in the denominator, I've got, let's see, this is going to be 2n plus 2 plus 3, so 2n plus 5, and then we'll have an x to the 2n plus 1 to join it down there. I'll deal with these 2n parentheses terms in a minute. Let me cancel out or reduce my exponential terms, though. Subtracting, I end up with just an x squared in the numerator, along with this 2n plus 3. This x to the 2n plus 1 gets completely canceled out, leaving us with just 2n plus 5 in the denominator. Now, as n approaches infinity, this plus 3 can be ignored, along with this plus 5 down here. So we have a 2n over 2n, which is just going to cancel. And at the end of the day, it's just x squared left inside the absolute value. So for my interval of convergence, I'm going to set this less than 1. And I have to actually isolate x before I can get any kind of endpoints here. So let me square root both sides. That gives me absolute value of x less than 1. And now I can rewrite this without the absolute value by writing negative 1 less than x less than positive 1. But I'll put a question mark here because I'm not really sure if that's my true interval of convergence. I have to test the endpoints since I used the ratio test rather than the geometric series test. So testing out negative 1 at x equals negative 1, plugging that in here, I've got, let's see, negative 1 to the 2n plus 1. 2n plus 1 is, let's see here, always going to be, I was about to say an odd power, but hold on a sec before I say that. We have a negative 1 to the n over here. So we have a negative 1 to the 2n plus 1. We have a negative 1 to the n. Well, we can add those exponents together and multiply those. So this is actually negative 1 to the 3n plus 1. And that's a horse of a different color. we still have a 2n plus 3 in the denominator here. All right, so this is, since this is an odd number here, this is going to alternate and also decrease in absolute value since the numerator is not growing but the denominator is. So it looks like alternating series test is going to prove this converges. Let's actually check out, though, what happens at our other endpoint at x equals 1, because I've got a feeling that I'm going to get another AST situation. So at x equals positive 1 now, this whole term 1 to the 2n plus 1 is just 1, so we can kind of ignore it. We really just have negative 1 to the n over 2n plus 3. Both of these alternate and decrease in absolute value to 0, which means that both endpoints converge by the alternating series test, which means that our true interval of convergence then is going to be negative 1 less than or equal to x less than or equal to 1. For this part of the problem, the Maclaurin series for g evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. Okay, they're just kind of handing that one to us. And then they're telling us the approximation of g of 1/2 using the first two non-zero terms, so x over 3 and x cubed over 5. They're telling us this comes out to 17 over 120. Show that this differs from the true value of g of 1/2 by less than 1/200th. So we need to use the alternating series error bound on this one. They didn't say we had to, but they're basically handing you the conditions for it. Since we have terms that alternate and decrease in absolute value to 0, which, I mean, we know we have that with 1/2 if you're plugging that in. You've got terms that are going to be going down, 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 increasingly down, and they're also alternating. But even if you didn't know that, they told you these terms decrease in value to absolute value to 0, and that it's an alternating series. So they're giving you this. Based off of that, we know that the error, which is what we're talking about with this 1 over 200 here, the error is going to be less than the absolute value of the next term. This is just our alternating series error bound. So we just need to figure out the next term, and the error will be less than the absolute value of that. So the next term, if we used the first two non-zero terms, the next term is going to come from this x to the 5th over 7. This is the third term. So we can write that the error is less than absolute value of this term with 1/2 plugged into it. So this would be 1 over 2 to the 5th times 7, and we'll put that in absolute value just to follow this form here. Well, this was a no calculator question, so let's see if we can estimate this here. So this is really 1 over 32 times 7. What's 32 times 7? Well, 30 times 7 would be 210. 2 times 7 is 14. So this is going to be 1 over 224. Now, since 1 over 224 has a larger denominator than 1 over 200, clearly this is a lesser fraction, a smaller fraction than 1 over 200. And since we've shown using this error bound that we have a number less than what they wanted, that proves what they were asking us to prove. On this last question, this was just kind of your reward for continuing to read, even if you had no clue about the first two, because you can do this without the first two at all. They're just asking for the first three non-zero terms in general term of a Maclaurin series for g prime of x. Well, folks, here's g of x. If you want g prime of x, just differentiate this. So we'll go term by term. Derivative of x over 3 is 1 over 3. Derivative of this next term, this is going to be negative 3/5 x to the second power. For this next one, we're going to have plus 5 over 7 x to the 4th. And they did want the general term. Well, here you have to recognize that the general term is what they're basically giving you inside the summation notation. So you just have to take the derivative of this summand here. So we're going to have a negative 1 to the n. That's sticking around as kind of a constant. We're going to multiply by our exponent of 2n plus 1, and we're going to subtract 1 from the exponent, so we'll have x to the 2n left over. So this is going to be then negative 1 to the n, 2n plus 1 over 2n plus 3 times x to the 2n. And there's our g prime.